Close your eyes and try to touch your index fingers together. You probably got close. That feeling of being slightly off, the tiny adjustment your muscles make without conscious thought, is a calculation. It's your nervous system computing an error signal. Every living thing does this. A plant's stem bends towards a light source, constantly correcting its trajectory based on where the photons are not. This isn't a decision, it's an algorithm. For a machine, this error isn't a feeling, it's a number. A value called the cost or loss, a pure mathematical measure of how wrong it is. Imagine this cost as altitude. Being perfectly right is the lowest point on Earth, sea level. Every possible wrong answer is a mountain, a hill, a towering peak. An AI, at the start, is dropped somewhere on this immense, invisible landscape, blindfolded. To learn, it doesn't see the whole map, it just feels the slope beneath its feet. This is gradient descent. It takes a small step in the steepest downward direction. It measures the slope again. It takes another step. Over and over, millions of times, it's just a blind mountaineer trying to find the bottom of the valley by always following the slant of the ground. But what if the lowest point it finds isn't the lowest point that exists? Our blind climber could descend into a small crater on the side of a huge mountain and, feeling flat ground in all directions, conclude it has reached the bottom. This is a local minimum. The AI has found an answer that is good enough, but not truly correct. To escape, algorithms were developed with concepts like momentum, essentially giving the climber enough speed to roll out of the shallow ditch and continue its search for the true deepest valley. This only works if you have an answer key to measure your wrongness against. But a baby learning to walk has no correct posture to compare itself to. The feedback is simpler. I am standing, or I have fallen. This is a different kind of learning. Instead of minimizing a detailed error score, the system tries to maximize a sparse reward. It's less about correcting a specific mistake and more about stumbling through actions until it finds a sequence that leads to a positive outcome. A robot arm might flail 1,000 times, but the one time it accidentally bumps a block into a box, a reward signal is sent, reinforcing that entire chain of clumsy behavior just a little. This creates a profound problem. If the robot arm made 500 distinct movements before getting the reward, which of those movements was the crucial one? Was it the initial lift, the swing, the final twitch? This is the temporal credit assignment problem. In a game of chess, did you win because of the brilliant final move or because of a subtle pawn placement 40 moves earlier? Sophisticated systems must find ways to let the final reward echo backward in time, strengthening the subtle, long-forgotten choices that paved the path to victory. When a human makes a mistake, the feedback isn't just a number. It's the sting of embarrassment, the burn of frustration, the spark of curiosity. Are these emotions just a highly evolved biological cost function? Is frustration simply your brain's momentum algorithm, pushing you to escape a local minimum of understanding? The cringe you feel when remembering a social faux pas is a powerful learning signal, far more memorable than a floating point number. It ensures you don't repeat the action, not by adjusting a weight, but by rewriting a piece of your story. An AI can play more games of Go against itself in an afternoon than humanity has played in its entire history. Yet a human toddler can learn what a dog is from seeing just 2 or 3 examples. They don't need to see 10,000 labeled images of every breed. This is the puzzle of sample efficiency. Humans seem to possess an incredible ability to generalize from almost no data. We don't just see pixels, we infer a model of the world. We understand dogness, the concept of 4 legs, a tail, fur, in a way that a machine trained on images does not. It recognizes patterns, but we build worlds. This leads to the final question. When an AI perfectly corrects its errors and can generate a flawless image of a dog, does it understand what a dog is? Or is it merely an impeccable mimic, a system with a cost function so close to zero that its predictions are indistinguishable from reality? When you learn from a mistake, you often gain an insight, a new perspective. The mistake illuminates something you didn't see before. Is the machine gaining insight? Or is it just getting better at predicting the next pixel on the screen, without ever knowing what a pixel or a screen actually is?
Monotony has grown fast. Nearly 2,700 people have watched in the last few weeks, yet less than 0.03% are subscribed. It would mean a lot if you joined by hitting subscribe. And again, thanks for watching.